In Chapter 3a, we learned the second law of thermodynamics. That is, for an isolated system, entropy should increase. Delta S is greater than 0 for spontaneous process. For reversible process, delta S equals 0. If it's a non-isolated system, then system entropy change, surrounding entropy change should add together and greater than 0 for spontaneous process. For reversible process, the total entropy should not change. Delta S total should equal to 0. So in order to predict spontaneity, we need to calculate both system and the surrounding entropy change. And sometimes it's inconvenient to calculate both. It turns out that under special conditions, the system entropy, surrounding entropy change added together can be combined into a single function. And that function under constant temperature, constant volume is called Helmholtz energy. Under constant temperature, constant pressure, it's called Gibbs energy. So in this section, we are going to introduce these two new state functions, Helmholtz energy and the Gibbs energy. The second law says for a spontaneous process, the total entropy should increase. So the delta S total should be greater than 0. If we define a new function called Gibbs energy, which equals H minus Ts, then this criterion becomes delta G is less or equal to 0. Okay, so this is the criterion for spontaneity in terms of entropy. And if we introduce the Gibbs energy function, then this becomes the new criterion. All right, so compare the two equations. One is greater than 0, increase. So delta S increase, but delta G decrease. So delta G is less than 0. If it's reversible, delta G equals 0. Okay, we're going to justify this in the next slide. Let's justify the new criterion. Under constant temperature pressure, Gibbs energy decrease is equivalent to the total entropy increase. So Gibbs energy is defined as H minus Ts, and the dG, the entropy Gibbs energy change, will be dH, the enthalpy change, minus TdS, the T times S change, which equals negative TdS minus SdT. Okay, so one is keep temperature constant, change entropy. One is keep entropy change, keep entropy constant, change temperature. Okay, and therefore delta G is delta H minus TdS minus SdT. Now, if we assume the process is constant pressure, so constant pressure enthalpy equals heat. If temperature is also constant, then dT is 0, so SdT is 0, and therefore delta G becomes dQ minus TdS. If we divide by temperature on both sides, then the left side becomes delta G over T, the right side becomes dQ over T minus ds. So temperature cancels each other. So you get TdS minus ds. Now ds is the entropy of the system. And dQ is the heat of the system, which is negative Q of the surrounding. Divide by temperature, that gives you the negative entropy change of the surrounding. And therefore the right side is negative the total entropy change. Okay? Now if second law says the total entropy should increase greater than 0, then the right side is less than 0 because you have a negative sign. And because temperature is always positive, that indicates delta G must be less than 0, delta G decrease. So this proves that the second law entropy increase is equivalent to, say, Gibbs energy decrease. All right. Also, remember, when we justify this equation, we assume temperature is constant, so SDT is 0, and pressure is constant, so enthalpy equals heat. Okay, so only when temperature, pressure are both constant, then we have this new criteria, all right, that is equivalent to delta S greater than 0. Okay, so note the definition G minus H, G equals H minus Ts. You can see here in this function, and S is the entropy of the system, and H is the enthalpy. The enthalpy represents heat under constant pressure, which represents the negative heat of the surrounding, or the negative entropy of the surrounding. And therefore, one function, Gibbs energy, represents both entropy of the system and negative entropy of the surrounding. And so you have a negative sign here, and therefore, when entropy increase, Gibbs energy decrease. So one function includes both system and the surrounding. Again, we see that in the Gibbs energy function, the enthalpy is used to represent the entropy of the surrounding. Okay, again, it's negative of the entropy of the surrounding, and entropy S is represents the entropy of the system. So in this way, one function includes both system and the surrounding. We just introduced a new state function, Gibbs energy, equals enthalpy minus Ts. And we show that in this function, under constant pressure, enthalpy relates to heat, which relates to the entropy of the surrounding, but it's negative. And S represents entropy of the system. And therefore, one function, Gibbs energy, represents both system and the surrounding entropy change, but it's negative. So when the entropy increase, Gibbs energy decrease. Now remember, this is under constant pressure, constant temperature. What if we want to find the function combine entropy, system, surrounding together under constant temperature and volume? Okay, so compared to Gibbs energy, under constant volume, we need a function that can represent heat, just like enthalpy represents heat under constant pressure. So here we define Helmholtz energy, which is U minus Ts. So under constant temperature, constant volume, internal energy delta U represents heat. Okay, and therefore one function delta A will represent both system and the surrounding entropy change, but it's also negative. So when delta S increase greater than 0, delta A less than 0. But the condition is it must be constant temperature, constant volume. So this is the new criterion for spontaneity under constant temperature, constant volume. Helmholtz energy less than 0 or equal 0 if it's reversible, and it's defined as U minus Ts. Gibbs energy has a very important property. Okay, if a reaction is spontaneous, then delta G under constant temperature pressure should be less than 0. And this spontaneous reaction can be harnessed to do useful work. The maximum non-PV work equals delta G under constant temperature, constant pressure. The prime here means the work is non-PV work. Okay, the work is not due to the volume change. So we use W, okay, to represent work done due to the volume change. So we can, if pressure is constant, we use negative pressure times volume change. So this is called PV work, okay, non-PV work is the work is not due to the volume change. For example, if a chemical reaction is spontaneous, we can use this reaction to build a battery, and the maximum electrical work, all right, the battery can generate equals the delta G of the chemical reaction. Okay, so the maximum non-PV work a system can achieve at a constant temperature pressure is the change of Gibbs energy or free energy. Okay, this non-PV work include the electrical work, biological work, so any work that is not related to volume change. Let's justify the fact that Gibbs energy change is the maximum non-expansion work under constant temperature pressure. So we start with the definition of Gibbs energy equals H minus Ts under constant temperature pressure. So if there's no non-PV work, in other words, the work is only due to the volume change, then we are familiar with the system. So let's just go over this. So under constant pressure, delta H equals heat, and therefore this is heat. So delta G equals dQ minus TdS. And according to the Clausius inequality, entropy always greater or equal to dQ over T. And so that means dQ minus TdS must be less or equal to 0. And that is the familiar criterion we already know. Delta G must be less than 0 under constant temperature pressure. And this is when there's no non-PV work. We call no additional work. Additional means work is not due to the volume change. Okay, so now let's look at the situation where we do have additional work. In other words, the electrical work, biological work, what happens? Okay, so under that condition, this is not true anymore because H equals U plus PV. So dH equals du plus PdV plus VdP. Okay, and the first law says du equals W plus Q. So U, internal energy change is work plus heat. But now we have non-PV work, non-additional work. And therefore, this dW we should write as 1 is due to the volume change. So the work is due to the volume change is negative PdV plus dW prime. dW prime means it's work due to the not due to the volume change. So you can see here negative PdV cancel each other, and if it's constant pressure, dP is 0, so delta H equals dQ plus dW prime. Okay, and compared to the left side, so if you only have work due to the volume change, then entropy is heat. But here, entropy is heat plus a additional work. The work is not due to the volume change. So now we calculate delta G. Okay, so delta G equals delta H, which is dQ plus dW prime minus TdS. Again, because of in Clausius inequality, we know dG, so this minus dQ minus TdS must be less than 0. So delta G must be greater or equal to the non-PV work. Okay, so that means that the maximum, okay, this equation means the maximum non-PV work is dG, is W. Okay, is the dW prime is the additional work or non-PV work. The maximum is the Gibbs energy change. In the last slide, we showed that under constant temperature, constant pressure, the Gibbs energy change equals the maximum non-PV work or the additional work. Now, if temperature is constant but pressure is not constant, okay, we can show that the maximum total work equals Helmholtz energy change. This total work includes the electrical work, biological work, and the work is due to the volume change. Now, because the work due to the volume change is usually not very useful, and so we are more interested in the non-PV work, and therefore delta G is more useful because this represents the maximum non-PV work, and we're going to focus on the Gibbs energy change. Let's summarize the second law of thermodynamics. So we first showed that if it's isolated system, the spontaneous process will increase entropy. Delta S is greater than 0. If it's reversible, then delta S equals 0. For a non-isolated system, then the system plus surrounding entropy should increase greater than 0 for spontaneous process. If it's reversible, the total entropy shouldn't change, so delta S equals 0. Okay? Now, under constant temperature, constant pressure, there is a state function called Gibbs energy. And this Gibbs energy is defined as H minus Ts. This function already includes entropy of the system and the surrounding, and they have opposite sign. So when entropy increase, Gibbs energy decrease, and therefore the criterion for spontaneity is delta G less than or equal to 0 under constant temperature pressure. All right, the equal sign applies when the system is reversible. Okay, and if temperature volume is constant, then there is a function called Helmholtz energy, which is U minus Ts. This function includes system surrounding entropy and the opposite sign. So when total entropy increase, the Helmholtz energy decrease under constant temperature, constant volume. And the Gibbs energy has a very important property, and that is Gibbs energy tells us the maximum non-expansion work or additional work. The work is not due to the volume change. And under constant temperature, the Helmholtz energy tells us the maximum total work of the system. Since under constant temperature, constant pressure, delta G less than 0 becomes the new criterion for spontaneity. So in order to know whether a reaction is spontaneous or not, we need to define the standard Gibbs energy of reaction. And this is defined as the difference in the standard molar Gibbs energy of the product and the reactants in their standard state at the specific temperature. So reaction, standard reaction Gibbs energy, the Gibbs energy of the product, and the standard Gibbs energy of the reactants. Now, this idea is similar to the way we define the standard reaction, standard enthalpy of reaction, okay, which is the standard enthalpy of product minus reactants, and the standard reaction entropy, okay, which is the standard entropy of the product minus standard entropy of the reactants. The standard reaction enthalpy is used to calculate heat, okay, and the standard reaction entropy is used to predict the spontaneity. However, remember, second law says the total entropy should be greater than 0. So even if we know the standard reaction entropy is greater than 0, doesn't mean the reaction is spontaneous. We need to know the standard, or we need to know the entropy change of the surrounding. And then we add these two, then we know whether the reaction is spontaneous or not. Now we have standard reaction Gibbs energy. So if standard reaction Gibbs energy is less than 0, then we know the reaction is spontaneous. We do not need to think about the system surrounding, and one function is enough. Okay. Also notice that when we calculate reaction enthalpy, we cannot use this equation. This is for definition. And to calculate, we defined a formation, standard formation enthalpy of the product minus reactants, because the standard enthalpy itself is not known. Okay, we don't know the standard enthalpy. Similarly, here even though we define reaction Gibbs energy by the standard Gibbs energy of product minus reactants, but these are unknown. Okay, we don't know, and therefore we are going to define the standard enthalpy of formation, standard Gibbs energy, formation Gibbs energy in the next slides, just like the enthalpy. All right. We define the standard Gibbs energy of formation as the standard reaction Gibbs energy of the formation of a compound from its elements in their reference state. And you can see the definition is very similar to the standard enthalpy of formation. Okay, the formation of the compound from its elements in their reference state. So by doing that, we can imagine the reactants decompose into elements, recombine into product, and we can easily derive this equation. The standard reaction Gibbs energy is the standard Gibbs energy of formation of the product minus the standard Gibbs energy of formation of the reactants. Just like the reaction enthalpy is calculated by standard enthalpy formation of the product minus reactants. Okay, so this is one way to calculate the standard Gibbs energy of reaction. So later we are going to introduce an alternative way to calculate reaction Gibbs energy at the standard state. You have seen this table already. The second column is the standard enthalpy of formation, and this is used to calculate the standard enthalpy of reaction. And the fourth column is the standard entropy, and this is used to calculate the standard reaction entropy. All right. And today we introduce the standard Gibbs energy of formation, and this is used to calculate the standard Gibbs energy. Okay, reaction Gibbs energy. Now note that the first two, these two, the standard formation enthalpy and the standard formation Gibbs energy, they all defined as the formation of the compound from its elements. So the elements formation enthalpy is 0. The formation Gibbs energy is also 0. So both are 0 for their elements. But for the entropy, this is not the formation entropy. It's the absolute entropy. So you don't see zeros here. Let's introduce an alternative way to calculate standard reaction Gibbs energy. So we start with the definition of Gibbs energy equals Ht minus Ts. So delta G should equals to delta H minus delta Ts. And the delta Ts is the change of Ts, which we can keep temperature constant, change entropy, and then keep entropy constant, change temperature. Now if temperature is constant, this is 0, so we won't have a TdS. And therefore delta G equals delta H minus TdS. If Gibbs energy is for chemical reaction, then enthalpy is also for reaction, entropy is also for reaction. So we have standard Gibbs energy of reaction equals standard enthalpy of reaction minus temperature times standard entropy of reaction. So how do we calculate this enthalpy of reaction, entropy of reaction? So the equation we already learned is the standard formation, enthalpy of formation of product minus standard enthalpy of formation of reactants. And we can find all this formation enthalpy in the table, so we can calculate this enthalpy. And similarly, we can calculate the standard entropy of reaction by standard entropy of the product minus standard entropy of the reactants. And so we have introduced this alternative way. We can calculate standard Gibbs energy of reaction. So which way is better? When do you use this method or the other method? Now it depends. So if we have the standard reaction enthalpy or standard entropy of reaction, then we use this second method. But if we have the standard Gibbs energy of formation, then we use the first method, which is the formation Gibbs energy of formation of product minus the Gibbs energy of formation of the reactants. Okay, so that's the first method, and this is the second method. Let's try the two methods to calculate the standard Gibbs energy of reaction for the following reaction. Carbon monoxide add oxygen forms carbon dioxide. So first try method 1. Okay, so method 1, we need use the standard Gibbs energy of formation, and this standard Gibbs energy of formation can be found from the table. All right, so the equation is the formation Gibbs energy of formation of product minus reactants. All right, so find the data. All right, plug in everything, and the answer is negative 257.2 kilojoule per mole. Okay, so what does this tell you? It's negative, and therefore the reaction is spontaneous at the standard state. CO, oxygen forming CO2 is spontaneous. Now let's think about the second method. All right, second method, we need use the standard enthalpy of reaction, standard entropy of reaction. So to do that, we need to find the table for formation enthalpy and the standard entropy. Okay, and so we can calculate the standard reaction enthalpy of reaction by the formation enthalpy of the product, which is CO2 minus CO. Note that oxygen is 0 for formation, and so that will give you the standard enthalpy of reaction. And then you calculate standard entropy of reaction by the product minus reactants. Okay, note that oxygen is not 0 because it's not a formation entropy, it's the standard entropy. So by doing that, you finally use the equation delta G of the reaction equals delta H minus T delta S. Okay, and I suggest you try it, and you should get the same answer as the first method. Now I want to remind you, when you use this equation, the final equation, and keep in mind the units must be consistent. Enthalpy is usually in kilojoule, note here kilojoule per mole, but entropy is usually in joule. All right, so you must pay attention to units. So most cases here you need to times 10 to the minus 3, otherwise you cannot get the correct answer. Sample question: how much energy is available for sustaining muscular and nervous activity from combustion of 1 mole glucose under standard condition at 37 degrees? Okay, so whenever you are asked to calculate the non-expansion work, so this work available to sustaining muscular nervous activity, this energy is a energy that not due to the volume change. So that's non-expansion work. And the second law says the maximum of this work equals delta G. So you are asked to calculate delta G of the reaction of this reaction. Glucose oxidation forms CO2 and water. Okay, so we have learned two ways to calculate the standard Gibbs energy of reaction, and we need to know what do we have, what we are given, what conditions are given. So here it says the standard reaction enthalpy and entropy are given. So we have standard enthalpy of reaction. We also have standard entropy of reaction, and therefore we are going to use the second method. All right. So the second method is delta H minus T delta S. Okay, and also note, pay attention. This is joule, so times 10 to the minus 3 give you 2,865 kilojoule per mole. So that means that one more glucose molecules can be used to do up to 2,865 kilojoule of non-expansion work.